acids and bases and acid-base equilibria. There are three acid-base theories. The first one is the Arrhenius theory, which deals with electrolytes. A strong electrolyte dissociates completely, whereas a weak electrolyte dissociates only partially. In the Arrhenius theory, a substance that produces hydrogen ions is called an acid, so HCl is an acid, and a substance that produces hydroxide ions is a base, so NaOH is a base. When you react an acid with a base, you get a salt and water. So this is a neutralization reaction in the Arrhenius theory. We can write an ionic equation for this reaction. If it is aqueous, we break it apart into ions. So HCl is aqueous. So in solution, it would form H plus and Cl minus. NaOH is aqueous, so it would produce Na plus and OH minus. On the product side, NaCl is aqueous, so Na plus plus Cl minus. And water is a liquid, so it stays together. We don't change that. When I cross out the spectator ions, those ions that remain unchanged on both sides of the equation, I get the formation of water. So in a neutralization reaction, I get hydrogen ions reacting with hydroxide ions to form water. Let me give you a couple more examples of the Arrhenius theory of acids and bases. AlOH3 reacting with H2SO4 to form water, and aluminum sulfates. My acid has hydrogen listed first, so my acid is H2SO4. My base has hydroxide, AlOH3, and you get a salt and water. Here's one more that follows the Arrhenius definition. So my acid has hydrogen listed first, that's Hi. My base has hydroxide, and I get a salt and water. So the Arrhenius definition's fairly easy to recognize. If you see H and OH, that is the Arrhenius theory. Bronsted-Lowry theory defines an acid as a proton donor and a base as a proton acceptor. So in this example here, we've got acetic acid reacting with water to form hydronium and acetate. You'll notice what happens. Acetic acid from the left side to the right side loses a hydrogen. So this is my acid. It loses a hydrogen. Water goes from H2O to H3O. It gains a hydrogen. So water is my base in this reaction. You'll notice I also have acids and bases on the product side. These are called conjugate acids and bases. If I go from H3O to H2O, I lose a hydrogen in the process. So H3O is called the conjugate acid. And if I go from acetate, C2H3O2, to acetic acid, I gain a hydrogen in the process. So acetate is my conjugate base. So this explains what I just went through. There are two acids and two bases in each Bronsted-Lowry reaction. Bronsted-Lowry is nothing more than a hydrogen transfer. Substances lose hydrogen, substances gain hydrogen as you go from left side to the right side and vice versa. The long arrow points toward the weaker acid and base. So let's look at this example here. We have NH4 plus NH2 minus, and we're forming NH3s. The longer arrow points toward the products. I couldn't do that on PowerPoint, but the longer arrow points toward the products. Identify the acids and the bases. And there are two acids and two bases. Well, my acids lose a hydrogen. So what loses a hydrogen? NH4 plus loses a hydrogen from the left side to the right side. And then my conjugate acid would be one of the NH3s. Bases pick up a hydrogen, so NH2 minus gains a hydrogen from the left side to the right side. And then also one of the NH3s would be the conjugate base. As far as which acid is the strongest and which base is the strongest, the longer arrow points toward the weaker acid and base pair. So my strongest acid is NH4+, and my strongest base is NH2-. The third acid-base theory has nothing to do with H+ or OH-. An acid is an electron pair acceptor, and a base is an electron pair donor. So with the Lewis theory, we're going to go back to Lewis structures and drawing those Lewis structures to determine the acid and the base. For example, let's say I have H+ plus OH-, and I want to determine the acid and the base as those produce water. Well, the Lewis dot structure for H+ has no valence electrons because the plus means we've lost the one valence electron that it had. OH- looks like this. Hydrogen has 1, oxygen has 6, but since there's a minus, we add an electron somewhere. And then they're going to form water. Which looks like that. So my acid wants electrons. It's the electron pair acceptor, so H+ is my acid. It needs valence electrons. My base is the electron pair donor. It has extra electrons. So OH- is my base, and you can see where the bond is formed when we form water. Let's look at this example here. What's the Lewis acid and the base in this reaction? F-, we're going to draw the structure F-. FS7, the minus means you add 1, so that would look like that. BF3, well, FS7, so I'll draw these 7 around the F's, and then boron is in group 3, so it's only got 3. So that's the Lewis structure for BF3, and it's going to form BF4-. Without drawing all the valence around the F's, you get a structure that looks like this. So the bond is formed right there. My base has extra electrons. My acid needs the electrons, so the base is F-. It has extra electrons that are capable of forming a coordinate covalent bond, and my acid, BF3. The boron only has 6 valence electrons. It wants 8, so it has space available for extra electrons to bond to. That's my acid. Water self-ionizes, which means that water, when left to itself, will produce a small amount of ions. So the water molecule will break apart into H+ and OH-. A better way to represent this is to take 2 molecules of water and break those apart into H3O and OH-. Now H3O is called hydronium. Hydronium and hydrogen are the same thing. Hydronium is nothing more than H+ added to water, and that will give you the H3O+, which again, hydronium. So they're interchangeable terms. When we multiply the product of the hydronium times the hydroxide ion concentrations, you get Kw, and Kw is a constant number. At 25 degrees Celsius, it's equal to 1 times 10 to the negative 14th. So Kw is called the ion product constant for water. We can do some math here. In pure water, we form 1 hydronium for every 1 hydroxide. And so in pure water, which is neutral, the concentration of hydronium and hydroxide are both 1 times 10 to the negative 7th. So pure water is neutral because H3O and OH are equal. If H3O is greater than OH, the solution is acidic, and if OH- is greater than hydronium, the solution is basic. So this is one way to tell whether a solution is acidic or basic or neutral.